Hello, in this lecture we will look at scheduling in the Linux operating systems. Essentially we will look at how the schedulers in the Linux kernel evolved over time. So the reference for this particular lecture is this particular book, Understanding the Linux Kernel, 3rd edition by Daniel Bowitt and Marco Sistasti. Linux classifies processes into two types. One is a real-time process and the other is normal processes. Essentially, a process could be either real-time or a normal process. Real-time processes are those which have very strict deadlines. For instance, they could be processes involving control of a robot or data acquisition systems or PIC controllers. Real-time processes should never miss a deadline and they should never be blocked by a low priority task. The other type of processes are the non-real-time processes, or generally called normal processes. So normal processes are of two types. They are interactive or batch. An interactive process constantly interacts with the users, therefore spends a lot of time waiting for key presses and mouse operations. So typically you could consider these as IO bound processes. When an input is received, the process typically should wake up within 50 to 150 milliseconds. If it gets delayed more than 150 milliseconds, then the system begins to look sluggish, in the sense that a user will not feel very comfortable using this system. On the other hand, batch processes are most closely similar to the CPU bound processes, which do not require any user interaction and they often run in the background. For instance, GCC compilation or some scientific operations like MATLAB fall into these type of processes. Once a process is specified as a real-time process, it is always considered as a real-time process, in the sense that once a user specifies that a process is a real-time process, then it is always going to be a real-time process, even though it does nothing but sleeping. On the other hand, for processes which are non-real time, that is the normal processes, it can behave as either an interactive process at one point of time or at other points in time as a batch process. Essentially, a normal process could behave as an interactive process or a batch process, and this behavior could vary from time to time. So in order to distinguish between interactive and batch processes, Linux uses sophisticated heuristics based on past behavior of the process to decide whether a given process should be considered a batch or an interactive process. So we will look more into detail about this. So looking from a historic perspective, over the years, starting from Linux 2.4 to 2.6, there was a scheduler which was adopted, which was known as the ON scheduler. Then from Linux 2.6 to 2.6.22, the scheduler was called the O1 scheduler, and the schedulers currently incorporated is known as the CFS scheduler. Now we will look at each of these schedulers in the following lecture. So let's start with the ON scheduler. ON scheduler means that the scheduler looks into the queue of ready processes, which could be at most n size, and it looks into each of these processes and then makes a choice about the process that needs to execute. So essentially, at every context switch, the ON scheduler would scan the list of runnable processes, compute priorities, and select the best process to run. So scanning the list of runnable processes is an order n job. Essentially, we have assumed that the ready queue has up to n processes present. So this obviously is not scalable. It's not scalable because as n increases in number, that is, as more and more processes or tasks enter the ready queue, the time to make a context switch increases. Essentially, the context switch overheads increase, and this is not something which is wanted for. So these scalability issues with the ON scheduler was actually noticed when Java was introduced, roughly the early 2000s, and essentially due to the fact that JVM the Java virtual machine, spawns multiple tasks, and each of these tasks are present in the ready queue. So, the scheduler would have to scan through this ready queue in order to make their choice. Another limitation of the ON scheduler was that it used a single global run queue for SMP systems. Essentially, when you had multiprocessor systems, as we've seen in the previous lecture, a single global run queue was used. So, this again, as we have seen, is not scalable. So, the next choice was something known as the O1 scheduler. The O1 scheduler would make a scheduling decision in constant time, irrespective of the number of jobs which are present in the ready queue. Essentially, it would take a constant time to pick the next process to execute in the CPU. So, this quite obviously scales even with large number of processes that are present in the ready queue. In the O1 scheduler, processes are divided into two types, the real-time processes and normal processes, as we have seen. So, the real-time processes are given priorities from 0 to 99, with 0 being the highest priority and 99 being the least priority of a real-time task. Now, normal processes on the other hand are given priorities between 100 to 139. So, 100 is the highest priority that a normal process could have, while 139 is the lowest priority that any process could have. And as we have seen before, the normal processes could be either interactive or batch. We will see later how the scheduler distinguishes between the interactive and batch processes. Now, we will talk about scheduling in normal processes, that is the non-real time processes. Essentially, the scheduling algorithm which is used is very similar to the multi-level feedback queue with a slight variation. Essentially, in this particular scheduler, there are 40 priority classes which are labeled from 100 to 139. And as we have discussed before, the lowest priority corresponds to the class 139, while the highest priority for the normal task is at 100. So, corresponding to each of these tasks, there is a ready queue. So, every process or every task present in the ready queue corresponding to a particular priority class has equal priority to be executed on the CPU. On the other hand, a process present in the 100th priority class has a higher priority to execute with respect to a process present in 102, that is a process present in the ready queue corresponding to 102. Now, based on this priority class, the scheduler maintains two such queues. So, one is known as the active run queues and the other one is known as the expired run queues. When a context switch occurs, the scheduler would scan the active run queues starting from the 100th run queue and going up to 139. It picks the run queue which has a non-zero or a non-empty queue present in that. So, for instance, over here it starts from 100 and picks this first particular process, and this process is executed in the CPU. At the end of the time slice, this process is put into the expired run queue. So, gradually you will see that as time proceeds and time slice is complete, the scheduler keeps picking out processes from the active run queues, executes them and puts them into the expired run queues. After a while, we would have a point where the entire processes in the active run queue is complete. Essentially, we come to the point that none of these priority classes have any processes with them. On the other hand, the expired run queue is now filled up, essentially because the scheduler has been adding processes to each priority class in the expired run queue. When this happens, the scheduler would switch between the active run queues and the expired run queues. Now, this is the queues which actually becomes active, while this becomes the expired run queues. Now, for consecutive time slice completions, the scheduler would pick tasks from this particular queue and execute these tasks. After execution, these tasks would be moved to this queue over here, which is now the expired run queue. In this way, there is a toggling between these two queues. All tasks present in one queue are executed and moved on to the tasks in the other queue. Then all tasks over here are executed, and after executing, the tasks are moved to the previous queue, and so on. So this process goes on continuously. The main reason for having such a technique in the Linux kernel's scheduler is that it prevents starvation. It ensures that every process gets a turn to execute in the CPU. Recall that we call this particular scheduler as an O1 scheduler. Essentially, this means it is a constant time scheduler irrespective of the number of processes present in the ready queues. Now, let us analyze how this particular thing is constant time. Now, if we recall, there are two steps involved in scheduling a process. First is to find the lowest numbered queue with at least one task present in that corresponding ready queue. Second, choose the first task from that ready queue. Now, how are these two things constant time? It is quite obvious that the second step is constant time. Essentially, we are choosing from the head of the queue, and that is obviously done in a fixed amount of time irrespective of the size of the processes. Next question is, how is step 1 constant time? So, essentially we know that the scheduler scans through all the priority queues starting from 100 and going up to 139 and chooses the lowest numbered queue which has at least one task. Essentially, it chooses the lowest non-empty queue. So, this does not seem to be constant time. So, how does the scheduler actually implement this so that the time taken to actually find the lowest non-empty queue is independent of the number of processes? In order to do this, the scheduler or the Linux scheduler makes use of two things. The first is a bitmap. This is a 40-bit bitmap which stores the run queues with non-zero entities. Essentially, this particular bitmap stores 0 for a class which has which is empty, and it stores 1 for a class which has non-zero entities. Second, it uses a special instruction known as find first bit set. So, this particular instruction, for example, there is a BSFL instruction on Intel, would look at this 40-bit bitmap and choose the lowest index which is non-zero. Essentially, this would give us the lowest numbered non-zero bit in the bitmap, and this corresponds to the lowest non-zero, or rather lowest non-empty priority queue. Now, let us look more at the priorities of the O1 scheduler. So, we had seen that priority 0 to 99 are meant for real time tasks, while priority 100 is the highest priority that can be given to a normal process, while priority 139 is the lowest priority that a normal process could have. Now, these are the ranges of the priorities for the normal process. That is, a normal process could have anything from a priority of 100 to a priority of 139. The priority 120 is known as the base priority and taken by default. So, whenever you start a program, for example, whenever you start an a.out program, it is given the priority 120. Now, you could change this base priority by using the command called nice. The nice command line is used to change the default priority of the process from 120 to something else. So, the command would look something like this way. So, nice minus n capital N dot slash a.out, where the capital N can take a value of plus 19 to minus 20. So, essentially the value that we specified here gets added to the base priority. So, for example, if I say nice minus n and plus 19 a.out, so my the process that I am starting will have a priority 120 plus 19, so that is 139. So, this would be the least priority that it could have. On the other hand, you could also specify a priority like nice minus n minus 20 dot slash a.out. So, this would give the process a priority of 100. So, this is the highest priority that the process could get considering that it is a normal process. So, these are the static priorities that the process could get during the start of execution. Besides the static priority, the scheduler also sets something known as the dynamic priority. This dynamic priority is based on heuristics and is set based on whether the process acts like a batch process or an interactive process. Essentially, it's set based on whether the process has more of I/O operations or is more CPU bound. So, the scheduler uses some heuristics which is present over here to compute the dynamic priority. Essentially, it takes the static priority which we have set, which is either 120 by default given at the start of execution, or the priority based on the nice value, and subtracts something known as a bonus and adds +5. So, it takes min of this, that is static priority minus bonus +5 and 139, and it then takes the max of 100 and this value. So, for instance, let us say we start the process with the default static priority, that is 120, and we give a bonus of say 3. So, then we have like 120 minus 3 plus 5, that is 122. So, min of 122 and 139 is 122, and you take max of 100 and 122 is 122. So, the dynamic priority for this particular example was 122. Now, the crucial thing is this bonus. So, how is this particular bonus set? So, essentially this bonus has a value between 0 and 10. If the bonus is less than 5, it implies there is less interaction with the user. Thus, the process is assumed to be more of a CPU bound process. The dynamic priority is therefore decreased. Essentially, the dynamic priority goes towards 139 of a low priority task. If the bonus is greater than 5, on the other hand, it implies that there is more interaction with the user. That is, the process acts more like a I/O bound process, and essentially the process behaves more like an interactive process. The dynamic priority is therefore increased, that is, it goes towards 100. So, you can take two examples. For instance, we have seen a bonus of 3, and we had seen that it resulted in a dynamic priority of 122, implying that it is more of a CPU bound process, therefore, is given a lower priority in the system. On the other hand, if you take a bonus of 8 and compute the same thing, you will see that the dynamic priority actually reduces. So, the crucial part is now how do we actually set the value of bonus. So, the bonus is in the scheduler is determined by the average sleep time of a process. The assumption here is I/O bound processes will sleep, or in other words will block more, therefore, should get a higher priority. So, therefore, I/O bound processes will have higher value of bonus. On the other hand, CPU bound processes will sleep less, therefore, should get a lower priority. If you look at this table, and if we see that the average sleep time for a process is greater than 200, but less than 300 milliseconds, it is given a bonus of 2. So, this is just a heuristic and followed as a formula in the kernel. On the other hand, if the process has an average sleep time greater than or equal to 800 millisecond, but smaller than 900 millisecond, we give it a larger bonus of 8. Thus, these processes process with a high value of bonus, that is, those processes which sleep more are considered interactive processes and given a dynamic priority which is closer to 100. On the other hand, processes which sleeps less are assumed to be CPU bound processes and given a bonus which is low, and as a result the priority is lowered, the dynamic priority is lowered, that is, it goes towards 139. So, how are these dynamic priorities affecting the scheduling algorithm? Essentially, if we come back to the active and expired run queues, the dynamic priority determines which queue the particular process would be placed in. For instance, when we choose a particular process to execute, say from the 100th priority class, and after it executes, its average sleep time is then used to compute the bonus, and thereafter used to compute the dynamic priority, and then this process is placed in the corresponding priority class. So, as a result, based on the average sleep time, when the process is placed back in the expired run queue, the class in which it is placed in would depend on its dynamic priority. So, besides the dynamic priority, there is also the time slice which is adjusted by the scheduler. Essentially, interactive processes have high priorities, but they are more of IO bound processes, and they are likely to have short CPU burst times. These processes, essentially interactive processes, are given the largest time slice to ensure that it completes its burst without being preempted. So, in order to set the time slice, we are using more heuristics such as this. So, essentially if the priority is less than 120, that is, it is an interactive process, then the time slice is given as 140 minus priority into 20 milliseconds. However, if it is more of a batch process, that is using more of CPU activity, then the time slice is set by the lower statement, that is time slice equal to 140 minus priority into 5 milliseconds. So, as a result of this, if you see this particular table, you see that if you have a static priority of 100, that is obtained by having a nice value of minus 20. So, it means that this is a interactive process and is given a large time slice of 800 millisecond. On the other hand, a process with a static priority of 139, that is 120 plus having a nice value of 19, it is given the lowest time slice or the smallest time slice of 5 milliseconds. So, thus we see that based on the priority of the process, the corresponding time slice given to that process is fixed. So, summarizing the O1 scheduler, it is a multi-level feedback queue with 40 priority classes. The base priority is set to 120, but modifiable by the use of this command called nice. The dynamic priority set by heuristics is based on the process's average sleep time. The time slice interval for each process is set based on the dynamic priority. So, the limitations of the O1 scheduler is as follows. So, the O1 scheduler uses a lot of complex heuristics to distinguish between interactive and non-interactive processes. So, essentially there is a dependency between the time slice and the priority, and the priority and time slice values are not uniform. That is, for processes with a priority of 100 compared to processes with a priority of 139, if you compute the time slices in these two ranges, you see that it is not uniform. If you look back in the table over here, you see from going from a priority of 100 to 110 has a time quantum of 200 milliseconds. However, going from 130 to 139 has a time slice difference of just 45 milliseconds. So, with this we will end this particular video lecture. So, in the next lecture we will look at the CFS scheduler, which is the latest scheduler or the current scheduler which is used in Linux kernels. Thank you.